So taking a look at the Paderborn bearing dataset, so it contains 26 damaged bearing states and 6 undamaged bearing states, healthy conditions. And the damaged bearings are divided into artificial and real damages. Two options are available where the damages are located: inner race and outer race. So that's it. So the transfer learning method will use a source as Paderborn dataset as its source, and Case Western Reserve University dataset as the target. We'll see. So the data from Paderborn is augmented using GAN to generate synthetic samples. Then the target domain is CWRU dataset. Um, in this paper, this is the target domain. So we already saw that CWRU dataset contains like 9 features. The target domain has limited data level data, making it challenging to train a model from scratch. That's why we do this transfer learning. So pre-training on the source domain, the model is first trained on the dataset using the augmented data generated by GANs. This step allows the model to learn general features and patterns associated with bearing faults. Then fine-tuning on the target domain using a small subset of the target data. This fine-tuning process involves adjusting the model's parameter to better fit the specific characteristics of the target domain. Fine-tuning the lower layer feature extractors are typically frozen, the convolutional layers for example, and only the higher layer classifiers are updated. So this approach helps retain the general knowledge learned from the source domain while attempting to the target domain's specific features. Then we have knowledge transfer. The process enables the model to leverage the knowledge gained from the source to improve its performance to the target domain. This approach reduces the dependence on large level datasets in the target domain. So there you go. Source domain, Paderborn, target domain, CWRU achieves a fault diagnosis accuracy of 97.52%. So another technique applied in this paper is the wavelet transformation. Continuous wavelet transform used to convert 1D vibration signals into 2D time frequency representations. So both temporal and frequency information both are presented. So 1D vibration signal is converted into 2D by So what is continuous wavelet transform? It uses a mother wavelet, a basis function, to analyze the signal at different scales and translations. It provides a time frequency representation of the signal, allowing the identification of localized features in both time and frequency domains. So it is a function of both xt, signal xt, and s. S is the scale factor, width of the wavelet. The integration is over tau, which is a translation factor, so it can be controlled. And the mother wavelet here is the complex Gaussian wavelet. Psi t is pi power minus 1 by 4 times e power I omega 0 t. Omega 0 is the central frequency or the base frequency, times e power minus t square by 2. So this is what forms the equation for CWT. So what is the use of this transformation? It captures non-stationary features since we are working with vibration signals. So CWT allows the model to capture these variations. Then we have denoising. Another thing is the feature extraction. This extracted time frequency representation is then fed into the asymmetric convolution network for feature extraction and fault diagnosis. So that's it. So why asymmetric convolutions? So they're hoping that the hope is that to be able to capture directional features as better than symmetric convolutions like 3 by 3. All right. Like it says here, horizontal convolutions can capture temporal features better 1 times 3. Vertical convolutions 3 times 1 can capture frequency features. So one on x-axis, other on y-axis, and square convolutions can capture combined temporal frequency features. So there are 4 attention heads used by the ASCIINET or asymmetric convolutional network in this paper. This is specified in the hyperparameter configuration table. Here you can see 5 hidden layers, 4 multi-head attention, 100 epoch, batch size of 64, learning rate 0.0001, and loss function is cross entropy loss. The optimizer is Adam optimizer. So there you have it, the 4 key components: generative adversarial network, transfer learning, Weber transform, asymmetric convolutional network with multi-head attention mechanisms, and together they come up to uh, with a hybrid approach for bearing fault diagnosis.